In this tutorial, we will be discussing the combined gas law. If we look at the three laws individually, we have Boyle's law, Charles's law, and Gay-Lussac's law. Boyle's law relates pressure and volume, Charles's law relates volume and temperature, and Gay-Lussac's relates pressure and temperature. We can combine all three of these variables into one equation called the combined gas law. If we look at just two of these individuals, if we look at the whole set of the combined gas law and just look at two variables at a time, for instance, if the temperature remains constant, that means the temperatures here would cancel out, and that would essentially give us Boyle's law. If the pressure remains constant, that means here and here there's no change, and that would equal out to be 1, and that gives us Charles's law. If the volume stays constant, that means for E1 and V2 for Gay-Lussac's law would cancel out to be 1. So by these three things combining, we can look at all three of those units at once. So remember that the combined gas is PV over T is equal to PV over T. So let's look at some practice ones. A gas has a volume of 675 milliliters, so that's going to be our V1, at 35 degrees Celsius. That's a problem because we need to add 273 to it to make it kelvins. And that comes out to be 308. And that's going to be our T1. And 646 millimeters of mercury. That's going to be our P1. What is the volume in milliliters? It's giving us our initial volume in milliliters, so that means we don't have any more conversions after that. Negative 95 degrees Celsius. This negative here is why you can never do this in degrees Celsius. It has to be in kelvins every single time. So we're going to go ahead and add 273 to this, and that comes out to be 178 kelvins. And a pressure of 802 millimeters of mercury. We started off with millimeters of mercury and we're ending in millimeters of mercury. So that's good. So 675 milliliters times 646 millimeters of mercury over 308 Kelvin. We're looking for the second volume. P2 is 802 millimeters of mercury at 178 Kelvin. Now, just like the other ones, the Charles's law and the Gay-Lussac's law, when we had a fraction going on, we're going to look at this as it's a ratio. So we're going to multiply these together. So 675 times 646 times 178. That comes out to be 77,616,900. If we want to focus on the units, which we always do, we have millimeters of mercury times milliliters times kelvins, because at this point we have nothing canceled out. The other direction, we have 308 times 802. That comes out to be 247,016. Our units here are millimeters of mercury and kelvins. And this is all going to be multiplied by X, which is going to be the volume. We want to get X by itself. So we're going to divide both sides by 247,016 millimeters of mercury dot kelvins. When we do this, the right side cancels out for all but X, and then the left side, the millimeters of mercury cancel out, and the kelvins cancel out. That leaves us with milliliters when we're done. And that comes out to be 300 and 14 millimeters. It's a longer question, but the process is still the same. Let's try this again. This one's a little bit more difficult because you have to be careful of the units. All right, a sample of helium gas has a volume of 0.180 liters, a pressure of 0.80 atmospheres, and a temperature of 29 degrees Celsius. Let's immediately change that 29 degrees to kelvins by adding 273. Let's just get that out of the way right now. That comes out to be 302 kelvins. What temperature in degrees Celsius? So once we figure out the equation, once we figure it out in kelvins, we have to subtract 273 to figure out the final answer. Will the helium have at a volume of 90 milliliters? Notice that it's asking us in milliliters, but our initial volume was in liters. That means we have to change the milliliters to liters. We're going to do this by dividing by 1,000. That becomes 0.090 liters. And a pressure of 3.20 atmospheres. It gave us the atmospheres on both sides of the equation, so we're okay with that. And then the N is constant, meaning that the amount of moles that are in there hasn't changed. All right, so let's go ahead and put this in the equation. 0.800 atmospheres times 0.180 liters over 302 kelvins is equal to 3.20 atmospheres times 0.090 liters over X. We're going to cross multiply. So that gives us $86.976. ATM dot liters dot kelvins is equal to 0.144 liters atmospheres times X. So to get X by itself, we divide by both sides. The atmospheres cancel and the liters cancel. That comes out to be 604 Kelvin. However, is asking for the final answer in degrees Celsius. So that means we need to subtract 273 from this number to get our final answer. And that comes out to be 331 degrees Celsius. And that's how you perform the combined gas law.